Yes, so this is work in collaboration with Maarten, Jonas, and Barbara. We are kind of spread across Delft and Amsterdam in the Netherlands. Let me kind of set the stage with a bit maybe more familiar thing than what's in the title. That would be the Qubit Hamiltonian optimization. You're given a Qubit Hamiltonian and you want to find its maximal eigenvalue. And we're going to restrict to mostly classical methods for doing that. So that's obviously not always possible, as you all will know. But let me just quickly review this. So for one local, most trivial case, that would be just kind of single qubit Hamiltonians, and it's also intuitions. They are non-interacting. It's a very easy problem, right? All the eigenstates are product states, in particular the ground state. Very easy to find it. Fantastic. So two local Hamiltonians are already hard, and they are NP hard to solve in this sense. And of course, maybe we want to solve something simpler. Maybe we want to reduce to to a more narrow family of Hamiltonians, or maybe we want to a bit weaken our demands. Maybe we want still to have some classical methods. Maybe we want to reduce also to classical states, such as product states, and try to get as close as possible to this maximal eigenvalue. And I'll call this lambda product max. This is not an eigenvalue per se. This is just a maximal value of this particular trace. And okay, so how close can we get? So this is an interesting question, academically at least. And this question was studied in some preliminary form already in the 80s, but kind of had some activity in the last 10 years as well. And the common theme in these results that you see here is that product states, sometimes they are very good, like in this Brandau-Haro result, and this relies on some specific property of the Hamiltonian, like it's a dense Hamiltonian or based on some kind of expander graph. But at least, even if you don't have these nice properties or you have some kind of hard requirements, at least you have order 1 approximation, right? So this ratio between this maximal value you can get with the product state and the maximal value and the actual ground state energy, you might say, is at least order 1. Fantastic. And of course, it kind of matters, right? I mean, when you consider these ratios, it matters whether your Hamiltonian is positive definite or traceless, right? Because you just like take in the ratio between the two, right? So if it kind of matters if your spectrum is bounded from below or no. But in this talk, we're going to mostly focus on traceless Hamiltonians. But you have to fix your kind of reference energy somehow, obviously. All right. So this talk is about fermions. So let me briefly review what fermions are. So fermions, as I'm going to refer to these operators as fermions, those are the Majorana fermion operators. And they have these basic properties that they're Hermitian, they're anti-commuting unless it's the same operator. If it's the same operator, it squares to 1. And they're traceless. And okay, so what's the space? What are these matrices, hopefully, right? If you have 2n Majorana operators like this, you can embed them in the 2 to the n dimensional space. So this is actually not so removed from the qubit problem in this sense. It has similar kind of complexity feeling to it, but not quite. And but if you want some kind of specific instance of what these Majorana operators might be, you could consider what's called the Jordan-Wigner mapping to qubits. So you can convince yourselves that these string operators would have the right algebra and all the nice properties. And this is a particular embedding into a specific 2 to the n dimensional space that you might be happy with. All right. Okay. So these are, fermions, you might have heard of electrons. Other fermions, they also have physical meaning, obviously, right? So they represent some systems composed of fermionic particles. Great. So, okay, it's interesting to consider the ground states of these fermionic systems. So what would be the equivalent of the one qubit Hamiltonians. Those would be the two local, actually, Hamiltonians in the fermionic case. They're a bit more complicated, but they're still easy to solve in the sense. The ground states are going to be Gaussian states. If you have never heard of Gaussian states, you could take this as a definition of pure Gaussian states. They are the ground states of particular quadratic Hamiltonians. This is good enough. And they are classically easy in the sense that they're easy to describe and they're easy to compute observables with. So they are, you might say, a fermionic equivalent of the qubit product states. So the first non-trivial problem for fermions would be those would be the interacting Hamiltonians, and those would be four local. I only consider terms of even weight because that's the thing that just makes most sense, at least from the physical perspective. Also, mathematical properties change dramatically if you consider odd terms. So I'm going to consider only even weight, and this is already NP hard. So a general for local is NP hard, and even if you make some reasonable constraints, this is a very hard problem. So, okay, maybe we can relax this problem a little bit as well. So maybe we are going to look across these kind of classical states, the Gaussian states, and try to get some reasonable value for this via optimization or whatever tricks we come up with. And okay, so let's maybe play the similar game for four local fermionic Hamiltonians as we did for two local qubit Hamiltonians. Now, okay, for four local Hamiltonians, people asked, do we still have this property that we had for two local qubit, that at least the approximation ratio is order 1? Okay, so very nice question. And people thought that it's possible, but it turns out that people thought that this is a reasonable hypothesis, or at least a possible scenario, but it turns out that this is not the case. There are examples of four local fermionic Hamiltonians that have vanishing approximation ratio with a guarantee. You can prove that Gaussian states can do much worse than, well, they get the energy that's much worse than the true ground state energy. These hard Hamiltonians are, well, so-called, the counter example to this hypothesis was the Sachdev-Kitaev model. It was introduced before in physics, and it has to do, well, people try to model, people try to use it as a toy model for this interesting thing called strange metals. People relate this somehow as a toy model to holography business in quantum gravity. So physicists care about it a lot. And people just tried, so it was tried in these two papers, at least by Halder, Tavakol, and Scafidi, and also Hastings and O'Donnell did this. They considered this Gaussian approximations for this model, and it showed that, they proved that Gaussian states, they just perform very poorly. All right, so our question here is, okay, so what are the kind of as weak constraints as possible that we can put on our Hamiltonian such that there is a guarantee that the fermionic Gaussian states, these kind of fermionic equivalents of product states, are indeed reaching this finite approximation ratio with a guarantee. Okay, I mean, this is a vague question. We just want to come up with some family. But if it's some broad family, then it's a good step in the direction of understanding this kind of complexity type of question. So we observed that this SYK model, I didn't define it for you, but the thing that you want to know probably is that it's a model where you have all-to-all interactions of weight 4. So any combination of 4 fermionic terms that you can come up with is in principle present in that model. So it's dense in that sense. And it also has some randomness in its interactions. So most statements come with high probability, with high probability kind of comment. So maybe if you sparsify these Hamiltonians and not consider dense Hamiltonians, but you consider few terms per fermion, then you can indeed prove that that the Gaussian states yield finite approximation ratio. And something like this was done for something along in the same direction was done for qubits by Hara and Montanaro. We are not going to use their methods, but it's in principle a similar reasoning on the qualitative level, I guess, or an intuitive level. It makes sense if you have a sparse Hamiltonian. Okay, so our results are as follows. First of all, we prove that the approximation ratio is finite for sparse Hamiltonians with all terms being weight q. The witness, the Gaussian state that actually reaches this finite approximation ratio can be efficiently constructed. That's actually how we give the proof. And we also prove the same statement for Hamiltonians with weight 4 and 2, not just all weight 4, but also weight 2 can be included, because the statement number 1 is if you have all weight q. So statement number 3 would be kind of physically relevant, obviously, because normally you have both. Then we also applied the theorems from point 1 to prove something about so-called sparse SYK model. It's not sparse by our definition because, let's say, the degree of every fermion. I will define precisely what we mean by sparse, but just to say it quickly here, while for us the degree of a fermion, which I will define, has to be finite, for sparse SYK, it's with high probability order log n. At least for some fermions, it is the case. So one has to do some extra work there to prove this. And the sparsified versions of SYK, they have the physical meaning, they have the physical relevance because the low energy properties are conjectured with some numerical basis, I believe, at this point, that are conjectured to be of similar type to the normal SYK. And finally, we extended the result of Hastings and O'Donnell to an arbitrary version of SYK for not just for local interactions, but for any weight that's bigger than 4, that is even. So in the remainder of the talk, I'm going to quickly guide you through the way we prove this statement for this sparse Hamiltonian with weight q, and try to explain the key idea there. So I'm going to introduce you to the building blocks of this construction, which are the matchings and the related Gaussian states, and then we're going to use it to give this proof. So I'll go by the method of nice pictures because we don't have so much time here and we are all tired. So imagine you have these 4 Majorana fermions, and those will be represented by vertices. And if we have a Hamiltonian term, then it will be, I'll draw like a kind of hyperface like this, but it is just like, just a surface like this. So if it's a 2-qubit term, it will be something like this. So if it's a 2-fermion term, it will be something like this. If it's a 4-fermionic term, it will be something like this. Now, if in the Hamiltonian you have 2 terms, then I'll draw something like this. Okay, fantastic. So let's move on. So this was how I will depict the Hamiltonians. Now, what is the k-sparse Hamiltonian? That's our definition. K would be the maximal number of terms that would be present in some of the fermions in the Hamiltonian. Okay, and here k happens to be 3 because, well, for this particular fermion in the middle, you have 3 terms, and you cannot find more than that in a fermion in this particular Hamiltonian. Okay, k can be different. We will care about cases when k is finite; it doesn't grow within. Now, here's the key tool, is the matching states. Okay, so here's some big technical definition. This is what a density matrix of a pure matching Gaussian state is. This factor G has to be plus or minus 1. So now at least you feel that there is something behind this, but you can just look at this picture. So there is a matching. You have, let's say, these 6 fermions, you pair them up, there's some perfect matching, and the state that corresponds to this particular matching on the picture would be something like this, right? You have G14 for this link 14, and you put this C1, C4 operator there, and you do the same for every other link. Okay, so if it's too scary, then you can just you can already have an idea how this looks. From this example. Now, the key property of these states, which, I mean, Gaussian states, like I told you, they are very efficient. You can compute all the observables with them very nicely. So, and here it's exemplified by this matching term consistency relation that we're going to talk about. I'll say that the term in the Hamiltonian, this square here, for example, and a matching are consistent if the kind of the induced matching, or let's say the subgraph of this matching that kind of induced on these vertices that are spanned by this interaction is itself a perfect matching of that interaction, right? So in this case, there are no lines going outside of this interaction, so these guys are consistent, this matching and this term. So, and the nice thing is that if they're consistent, then the expectation value of this term with the state is just going to be a product of the weights of this particular link. There is some sign prefactor, but you shouldn't worry about that, and proportional to the j. Now the nice thing is that we can just, if we construct a state, we can pick our own g, right? And depending on what g we pick, we can have a plus or a minus sign in front of the absolute value of j if we know the sign of j. So that's going to be our tool. Now this happens if these terms, if the term and the matching is consistent. If they're inconsistent, it's even nicer. The contribution is 0. So if they're inconsistent, like in this example, this trace is 0, so well, it's 0. Okay, so this is very nice. If the matching and term are inconsistent, this is very simple. Fantastic. So let's do an exercise for this Hamiltonian. Okay, so in this Hamiltonian, we have these 3 terms. Now let's draw this matching. For this particular matching, you might notice that this square 1, 2, 3, 4 is inconsistent, while the other 2 terms are consistent with this matching. What does this give us? It gives us that the contributions from these 2 terms that I highlighted in blue are there, and they're proportional to these products of the g's, while this one doesn't enter the trace. Okay, and nicely enough, we try to maximize the energy, right? So we're going to pick our g's such that the contribution from this trace rho h is as high as possible. And in this particular case, it's possible because we have enough freedom here, and we can, in particular, we can choose those weights in the rho to be such that this trace rho h is as high as it's possible for this particular scenario, right? So this is fantastic. So now, after this small exercise, I'm going to guide you through the general construction. Okay, so just to remind you, this is what we want to prove. Before it was omega of 1. Now I give you a bit more detail. It's 1 over k squared q squared. K and q are finite, they don't grow with n, so it's the same as order 1, but it's probably nice to have also the dependency for k sparse q local, strictly q local Hamiltonian. All right, so this is our approach. Let's highlight some subset of terms in the Hamiltonian, and okay, so fantastic. Let's draw a matching such that it is consistent with the subset of terms and inconsistent with the rest. So we just like completely kind of like make a really bad job at being consistent with the rest, and then we're happy. Okay, and of course you have to prove that it's all possible, fantastic, but this is what we do. But trust me, it's possible under certain conditions for S prime, which I'm going to explain to you now. Now, we construct a Gaussian state based on that matching, and we will only have contributions from this highlighted part of the Hamiltonian, right? And the rest will be 0 because it's all inconsistent. Now, we want to maximize the contribution from the Hamiltonian, and if these green terms are sufficiently far apart, right? I write there well separated S prime, right? So this is going to be our condition S prime. I'm going to spell it out in a second. Then, if these g's are independent, then we can just like decide on our own signs in every term, and then we're going to have positive contribution with a guarantee. Now, our second demand, which will actually solve our problem completely, is that this sum of these absolute values of j's is bigger than 1 over some factor q of the sum of the absolute values of j's over the entire system, over all the terms in the Hamiltonian. And this solves our problem because the sum over all the absolute values of j's is bigger than the total, than any maximal eigenvalue you can possibly imagine. This is just a very, very generous upper bound. And if S prime satisfies the demand, and this is this demand, then our proof is finished because you can just write another inequality, and that's exactly what we tried to prove. If Q is 1 over K squared Q squared, we are done, we have a finite approximation ratio. Okay, so in the remaining 1 minute, I'm gonna probably quickly skim through why it's possible, but this is your takeaway message. If the Hamiltonian is sparse, then it is possible. Now, why it's possible? So this is our wish list. We want S prime and be well separated at the same time, having a very large energy here. Now, these two conditions are clearly in tension. They are not very friendly to each other, because if it's well separated, then probably you will not have a very big energy. Now, what does it mean well separated? Okay, so this term, let's say it's in our set. Now, this is bad, this is too close. This is also bad because they kind of share a neighbor. Now, this is okay. Okay, so this is literally the condition. So what do we do now? If it's a sparse Hamiltonian, as a sparse, that's what it means, I remind you. So it has like finite amount of terms per fermion. Then we can just color it up. Okay, we can color this Hamiltonian such that we have a bunch of colors, and the number of those colors are going to be K squared Q squared, such that inside each color it's all well separated. Then we maximize this value inside the color. So we pick a color such that this thing is maximized. And if you have a small amount of colors, with a guarantee you have this approximation ratio. And that's exactly what we wanted to prove, so we're done. So this coloring thing solves it all for us, and it's possible when the Hamiltonian is sparse. Fantastic. So let me conclude. So we have finite approximation ratio for sparse Hamiltonians. We have an efficient deconstruable witness, because all of that is an efficient algorithm. This extends to some not quite sparse Hamiltonians, and we also extend the Hastings-O'Donnell algorithm, but for that you have to go back to the paper and read. All right, so I'll put these future directions on the slide, and I'll take your questions. Thank you so much.
Thanks for the nice talk. Any questions? Yes.
Thanks for a very nice talk. So regarding the relation between like the fully so the SYK model has a dense and a sparse one, it seems that when you sparsify it becomes more classical. And then could you comment on if the original Hamiltonian is supposed to be very quantum, and how does the quantum hardness get lost in this process, or is this because you cannot get so what happens?
So I guess strictly speaking, this does not make it completely classical, in a sense that, well, we give just a finite approximation ratio statement, and we also neglect some parts of the Hamiltonian in the process. So maybe getting to the exact ground energy is not necessarily easy still. So we only make it classical in this sense. And they do have evidence, the physicists, the high energy physicists do have evidence that there are some Goldstone modes and stuff like this. So I wouldn't be as strong as to say this, but people did, Hastings-O'Donnell, they did ask the question, okay, when they prove this non-finite approximation ratio, does this hold for sparse SYK? Well, we show that it doesn't.
Thank you for your talk. And I wanted to ask if that method also works if you have 4 fermion terms, but they come pairwise on the same side. So like a Heisenberg chain, for example.
Yes, absolutely. The Heisenberg chain is a sparse Hamiltonian, so everything will go through, of course.
So I was wondering. So as you mentioned, this sparse SYK model is supposed to exhibit some of the essential features of the dense version thereof, and it's important in black hole physics and holography and so on. So could you say a little bit about what the interpretation of this maximum eigenvalue would be in, let's say, the black hole, or more broadly holographic interpretation of this model?
I guess people mostly care not about the energy per se, but about the properties of the state, as usual. And yeah, the value of the energy, I don't think holds any particular value. But it does matter. Like if you approximate the state very nicely, then of course you can use that state. But yeah, these are very modest approximations that you have to remind.
Right, but you wouldn't expect that it somehow relates to, let's say, a black hole mass. Just
I wouldn't know. I mean, I don't know even about normal SYK. I'm not. Yeah, I cannot.
maybe the strange metal interpretation then.
Yeah, okay, we can talk about it later.
Okay, maybe one final question. How do I get there?
Come on, you're from Amsterdam. You can, okay, not no longer from Amsterdam. So.
Yeah, I was curious. Is there also a version of this for bosons somehow with in some nice parameter range? Do you know where you also approximate with Gaussian states?
Yeah, I think for bosons, yeah, it's not immediately obvious to me. Yeah, I would, yeah, for like genuine bosons, non-spins, right, non-qubits. Yeah, I wouldn't know immediately. Yeah, I guess I think it's a very good question, but yeah.
Okay, so with that, let's thank our speaker again.
Yeah, thank you.